नमस्कार, सुस्वागतम, केम छो, आदाबार्स, गुड आफ्टरनून। आप सभी का पीआरएल के अमृत व्याख्यान में स्वागत है, अभिनंदन है। A very warm welcome from me, Anil Bharadwaj, for the PRL का अमृत व्याख्यान. Today is the 68th व्याख्यान of the 75 episodes series of Vyakhyaan, which is being organized as a part of PRL's 75 years of legacy and history in fundamental physics and space sciences. Established in the year 1947 by the father of Indian space program, Dr. Vikram Sarabhai, the PRL's Platinum Jubilee coincides with India's 75 years of independence. Hence, it's a joint celebration of the development of science and technology in India by PRL under the banner of PRL का अमृत व्याख्यान. Today, we have yet another very distinguished Vyakhyaan with us, Professor Arnab Choudhuri, who is a professor at Department of Physics at Indian Institute of Sciences in Bangalore. And he is going to talk to us on the topic, an enigmatic fluid flow inside the sun, the meridional circulation. Today, we also are having the second Dr. Arvind Bhatnagar Memorial Lecture. And Professor Arnab Choudhuri is the most apt person for doing it. Being a solar physicist, Arnab Bhatnagar established the Udaipur Solar Observatory, and Professor Arnab Choudhuri actually works in the area of the solar physics. So we greatly thank Professor Choudhuri for accepting our invitation and to be with us at today's PRL Kamrit Vyakhyaan as well as second Arvind Bhatnagar Memorial Lecture. Our PRL Kamrit Vyakhyaan is a series of lectures I was just mentioning, which is being celebrated as a part of PRL's Platinum Jubilee as well as Azadi Kamrit Mahotsav. I would now request my colleague Professor Narita Shrivastava to kindly brief our audience about the Arvind Bhatnagar Memorial Lecture. And subsequent to that, Dr. Pallam Raju will formally introduce our today's Vyakhyaan to the panel at WebEx, as well as those who have joined us live on.
Hello, can you hear me?
Yes.
And see my slide. This is just one slide. Can you see the slide?
Yeah, we can see your slides. Go ahead.
Okay, thank you. So thanks, Professor Bharadwaj. It is indeed my honor and privilege to say a few words about Dr. Arvind Bhatnagar, founder of the Udaipur Solar Observatory, and in whose memory we are having today's Vyakhyaan. Dr. Arvind Bhatnagar was born in Byawar, Rajasthan on 19th November 1936, and after completing his masters in physics, he joined the UP State Observatory, Nainital, in 1958 and worked there until 1961. He was awarded a PhD degree in solar physics in 1964 from Agra University for his research under the supervision of Professor M.K. Venubapu at the Kodaikanal Observatory. His thesis, in fact, was based on Evershed effect on sunspots, based on observations recorded at the Kodaikanal Observatory with the Solar Tower Telescope, in conjunction with the littrospectrograph. Dr. Arvind Bhatnagar was awarded the Carnegie Fellowship of USA during 1968 to 70. Later, he joined the Big Bear Solar Observatory of Caltech as resident astronomer. In 1972, he returned to India to establish this unique solar observatory in the middle of Lake Fatehsagar in Udaipur. This observatory became internationally well known as one of the major centers for solar observations. And Dr. Arvind Bhatnagar played a key role basically for helioseismology studies in India when USO got selected as an observing station for the 6-station Global Oscillation Network group sites, which is known as GONG site. And GONG instrument since then has been providing observations of the sun and has already completed 27 years of its operation. Parallelly, to initiate and prepare Indian scientists for research in this new area of helioseismology, he organized the first tutorial workshop, international tutorial workshop in helioseismology in PRL in January 1993. Besides his research publications, which are well known, Dr. Bhatnagar wrote a very fascinating book on fundamentals of solar astronomy with Bill Livingston. He was also elected Fellow of the National Academy of Sciences, Allahabad, and also a founder member of Astronomical Society of India and a member of the IAU, that is International Astronomical Union. His work for public outreach for astronomy has had many facets. As many of you are aware, he was also the founder director of Nehru Planetarium, Mumbai from 1976 to 1978, and served as an advisor to many planetaria in the country, that is Allahabad, Delhi, and Baroda. During the 1995 total solar eclipse, Dr. Bhatnagar undertook a very adventurous experiment by supervising to photograph the corona from the height of 25 kilometers from the cockpit of a MiG-25 plane of Indian Air Force, following the path of the eclipse. He was also committed to protection of environment of Udaipur, which is famous for its lakes, and Dr. Bhatnagar started a novel project in 1996 called Shuchi, that is Swachh, Healthy, Urban, Clean and Hygienic Environment Abhiyan in Udaipur for solid waste management through public participation. He was also appointed as one of the High Court commissioners to monitor the protection of the lake system at Udaipur. Those who worked with him or knew him, they will remember that his dedication and passion for astronomy was infectious. He was also a gifted observer and had the natural ability to enthuse all, young and old, specialist and common man alike with the excitement of observational astronomy. To honor his contributions to solar physics, the Dr. Arvind Bhatnagar Memorial Lecture is being organized every year. We are very honored and happy that the second memorial lecture in this series will be given today by Professor Arnab Choudhuri of Indian Institute of Science at Bangalore, who is also a renowned solar physicist. I request Professor Pallam Raju, Dean PRL, to formally introduce Professor Rai Choudhuri and invite him to give the second Dr. Arvind Bhatnagar Memorial Lecture. Dr. Pallam Raju, please.
Thank you, Professor Nandita. It's indeed a great honor and a pleasure for me to introduce today's speaker, Professor Arnab Rai Choudhuri. Professor Rai Choudhuri obtained his BSc from Presidency College, Kolkata, and MSc from Indian Institute of Technology, Kanpur. He did his graduate studies at the University of Chicago, wherein he received the Valentin Telegdi Prize for topping the physics candidacy examination and worked under the supervision of Professor Eugene and Parker, obtaining his PhD in 1985. He joined the faculty of Indian Institute of Science in 1987, wherein he worked until his superannuation in 2022. Professor Choudhury's research expertise is in astrophysical magnetohydrodynamics, problems specifically to the sun. He has made significant contributions to the research on the formation of sunspots and also solar dynamo modeling. Professor Choudhury is the author of two graduate textbooks, The Physics of Fluids and Plasmas, An Introduction to Astrophysics, and Astrophysics for Physicists. Both are Cambridge University Press publications. They came in 1998 and 2010. And they are used in many universities around the world as reference books. He has also written popular science books on nature's third eye, the story of sunspots. Professor Choudhury has been an Alexander von Humboldt Fellow and J.C. Bose National Fellow. He is also an elected Fellow of the Indian National Science Academy, Indian Academy of Sciences, and the World Academy of Sciences. Professor Choudhury has been awarded the S. Chandrasekhar Prize of Plasma Physics for the year 2022 by the Division of Plasma Physics, Asia Pacific Physical Societies, and for his contribution in developing flux transport and solar dynamo models of the 11-year sunspot cycle, and for using this model to provide theoretical explanations of so many solar phenomena, as well as the first successful dynamo-based prediction of the sunspot cycle. It's indeed a great pleasure and honor for me to formally invite Professor Arnab Choudhuri to deliver the 68th PRL Amrut Vyakhyaan and the second Dr. Arvind Bhatnagar Memorial Lecture. And he'll be talking to us on a very exciting and intriguing problem. And the title of the talk is An Enigmatic Fluid Flow Inside the Sun, the Meridional Circulation. With this brief introduction, I would request Professor Choudhuri to please take on from here.
Okay, so yeah, thank you, Professor Palam Raju, for the kind introduction, and I am grateful to Professor Nandita Srivastava for inviting me, and also thank Professor Anil Bharadwaj for the kind words. So let me now see if I can share my screen. So yeah.
Yes.
So can you see my screen and my pointer?
Yes, yes, we can. Please go ahead.
Okay. So it is a great privilege and honor for me to give this Dr. Arvind Bhatnagar Memorial Lecture, because Professor Arvind Bhatnagar has been one of my scientific heroes. So the way he set up this Udaipur Solar Observatory, fighting against many obstacles, that is almost like the stuff of legends. And I had the privilege of knowing him personally and received tremendous support and encouragement from him in the early years of my career in India. And perhaps most of the persons in PRL know about his scientific contributions, and Nandita also mentioned. So I would like to specially make a comment about his phenomenal ability as a science communicator without parallel. So Nandita also mentioned that. So around 2005, some of us organized in India-China Solar Physics meeting in Indian Institute of Astrophysics, and we invited Professor Arvind Bhatnagar to give an evening public lecture. And in those days, we did not have facilities for recording lectures easily. So I don't think that the lecture was recorded, or if there exists any recording of that extraordinary lecture. But for those of us who listened to that lecture, probably we would never forget it. And I can undoubtedly say that this was the best public lecture on the sun given by any Indian I have ever heard. Okay, so today I am going to talk about the meridional circulation in the sun. So to those of you who are not familiar with the term meridional circulation, this term may suggest something sort of complicated or technical. So my first job is to tell you what is this meridional circulation, and also reassure you that this is actually some phenomenon with which all of you are familiar, even though you might not have known this term meridional circulation. So let me explain it by considering an example from our Earth's atmosphere. So the equatorial region of the Earth gets heated by the sun's rays, and so the air in this equatorial region becomes hotter and lighter, so it rises up. So the colder air from higher latitudes rushes to this equatorial region, and the hot air which rises up, that then spreads towards higher latitudes and becomes colder and comes down, and thereby setting up this kind of circulation pattern. So this sort of circulation of a fluid in a meridional plane, that is called meridional circulation. So now, how can we develop a theory of this meridional circulation? So certainly it requires fluid mechanics, because we are dealing with fluid flows, and also we need thermodynamics, because we have to deal with this heating of air and it becoming lighter. So I'm sure all of you know the basics of fluid mechanics and thermodynamics. So I can throw a challenge to you that try to set up the basic mathematical equations of this meridional circulation. So it may seem something very straightforward that hot air rising up and the cold air rushing there. But if you try to set up the equations, then you will realize that this problem is much more complicated than you might expect at the first sight. So the best way to proceed is to consider this quantity vorticity, which is a curl of velocity. And if we have a circulation like this, then certainly there will be a component of vorticity perpendicular to this plane in the phi direction if you are using spherical coordinate. So one thing you can do that starting from basic fluid dynamics equation, you try to obtain an equation for the phi component of vorticity, and then you will find that there will be some source terms which are driving the circulation, and there would be some damping terms due to, I think, viscous dissipation. And later, after a few minutes, I shall show the actual equation, and we'll see that it is exactly of this form. And here is the plan of my talk. So first I shall present the observational results of this meridional circulation at the solar surface and also in the interior. And then I shall come to the question of how we build a theoretical model of the meridional circulation. And we shall see that it is intimately connected with the theory of another large-scale flow in the sun, the differential rotation. And this intimate connection between the two will be illustrated very clearly when I discuss this theory of what is called a near surface shear layer, a layer just below the sun's surface where this differential rotation changes over a very short distance. And finally, I shall discuss the variation of this meridional circulation with the 11-year sunspot cycle and point out how one can model it theoretically. So first, let us begin with the observation. So you all may know that sunspots are regions of strong magnetic field on the solar surface, and Babcock discovered that even outside sunspots there is sort of a weak magnetic field on the solar surface. Of course, nowadays we know that it is not actually a weak magnetic field, but it's a magnetic field concentrated in some small flux tubes of size a few 100 kilometers and a magnetic field strength 1000 Gauss. But in the low resolution magnetograms of the earlier time, these flux tubes were not spatially resolved, and it seemed like a smeared out weak magnetic field. And in the 1960s, several observational astronomers discovered that there would be a latitude belt on the surface of the sun within which this weak field would have a particular sign, as I have shown here. And with the progress of the solar cycle, it seemed that these belts drifted poleward. So at certain time, you may see a belt like this, and you may, if you do an observation a few months or years later, you will find that this belt has shifted to a higher latitudes, and after some time, it will be shifted even to higher latitudes towards the pole. So this was the first evidence that there is a kind of plasma flow at the sun's surface, which is carrying this weak magnetic field poleward. After it was first discovered in 1960s, there was some debate whether this was a sort of a temporary flow caused by some local effect, or is it a long-lasting flow. So I may point out that this question was settled by some work done from India, from Indian Institute of Astrophysics. So let me mention about that. So if you take a photograph of the sun in an H-alpha filter, which is regularly done in Udaipur Solar Observatory, then you will find gases a little bit above the sun's surface. And here I show an H-alpha photograph of the sun. So here you see some structure above the sun's surface, which is called a filament. and it turns out that these filaments form above neutral lines. So in this case, you see that there is this sort of a neutral line on the two sides of which this magnetic field has opposite signs, and these filaments form over these neutral lines, and so they indicate the position of this neutral line. So if you study how the positions of these filaments change over a few months or years, then you can you understand how this neutral line is changing and how this magnetic field is evolving. And in Kodaikanal Observatory, these H-alpha photographs of the sun have been taken almost every day from the beginning of the 20th century. So Professor Shivaraman of IIA and his Russian collaborator Makarov analyzed these old H-alpha plates of Kodaikanal Observatory, and from that concluded that this meridional circulation has been there at least from the beginning of 20th century, or more than for about 100 years at least. And this maximum amplitude at mid latitude is found to be about 20 meters per second. And we do not expect that the plasma which goes towards the pole to pile up near the pole. So what happens to the plasma? There must be some path underneath the surface through which the plasma again flows back from the polar region to the equatorial region. And where is that? And here I show a cartoon of what the interior of the sun is expected to be like according to theoretical astrophysicists. So at the center of the sun, energy is generated by nuclear fusion, and this energy is transported outward. And it turns out that this region from 0.7 solar radius to the surface is subject to convective instability. So in this region known as convection zone, heat is transported by convection, and we believe that it is the turbulent stresses in the convection zone which are very crucial for driving these large-scale circulations like meridional circulation and differential rotation. So our guess is that meridional circulation would be these large-scale flows would be confined in this region. And so this most obvious expectation is that that the profile of meridional circulation would be in the convection zone would be as indicated by this blue contour. So it is from equator to the pole at the surface, and then at the bottom of the surface we would have a return flow from the polar region to the equatorial region. And one very important question in solar physics is that what produces the solar magnetic fields and 11-year sunspot cycle. So the theory with which we try to explain that is called dynamo theory. And some of us have been involved in developing a kind of dynamo model known as the flux transport dynamo model, in which this meridional circulation plays a very important role. So this is a subject on which I have worked for many years. It's rather close to my heart, and my Chandrasekhar Prize was also given primarily for this work on flux transport dynamo model. But it is a subject of a completely different full colloquium. So today I shall not get into the details of that model. So I shall only mention that this flux transport dynamo model gives results agreeing with observation if we assume that the meridional circulation is of this type with a return flow at the bottom of the convection zone. So since this gave a very good agreement with observation, so for more than a quarter century, some of us have been arguing that the meridional circulation of the sun must be like this. But for years, there were some harsh critics who were telling us that we were building castles in the air. So there was no evidence that the meridional circulation was really like this, and the flux transport dynamo model could not be correct. So I'm glad that within the last few years, this issue is being settled by helioseismology. And in a lecture given at PRL, I presumably don't have to explain what is helioseismology, the study of solar oscillations. As Nandita mentioned, that due to the visionary initiative of Professor Arvind Bhatnagar, this Udaipur Solar Observatory became a hub of this helioseismology network, GONG, Global Oscillation Network Group. And through helioseismology, it is possible to study these various fluid flows underneath the sun's surface. So when helioseismology was first applied to study meridional circulation, the first results were for flows just below the sun's surface. So as you go deeper down, the helioseismic inversions become more uncertain. So till a few years ago, there was a big divergence in the results of different helioseismology groups. So here I show an interesting plot prepared by my good friend Junwai Zhao. So he used the same color code to represent the results of different helioseismology groups. So these are plots of V theta, the important component of meridional circulation. And if this circulation is poleward, then red color is used. And if it is equatorward, then then blue color is used. And here you can see that this results of different groups diverge quite a bit. So this is the result due to Rajaguru and Antia, who found evidence of this equatorial flow at the bottom of the convection zone and concluded that this meridional circulation pattern is very much like what is needed in flux transport dynamo models. But there are other groups like Zhao et al. Who claim that this return flow takes place in the middle of the convection zone, and there are more cells of meridional circulation at the bottom. And within the last few years, this field is converging. Some time ago, a very thorough paper by a large number of authors, Gizzo et al., came out in Science by analyzing various kinds of data more exhaustively, and they more or less reconfirmed these results of Rajaguru and Antia, so that this meridional circulation is like this as required in flux transport dynamo models. So this provides a big support for the flux transport dynamo model. And I may mention that about a decade ago, when there was this debate about the nature of meridional circulation. So at that time, with Gopal Hajra and Vidya Karak, we looked at this problem whether the flux transport dynamo could work with more complicated meridional circulation. So we put some arbitrarily complicated meridional circulations in our code. So as you see here, these are streamlines of this arbitrarily complicated meridional circulation. Red corresponds to clockwise circulation and blue corresponds to counterclockwise circulation. So we found out that even with such complicated circulation patterns, this flux transport dynamo can be made to work if one criterion is satisfied. At the bottom of the convection zone at the lower latitudes, you have to have a equatorial flow to give results matching observations. So anyway, now probably we do not have to bother about these issues anymore, since the helioseismology has established that this meridional circulation pattern is like what we had been assuming in flux transport dynamo model for more than 25 years or so. So now let us come to the theory of what may give rise to this meridional circulation. So within the convection zone, hot blobs of gas would be rising and cold blobs of gas would be sinking. And certainly these moving blobs would be affected by the Coriolis force of the sun. So the sun is rotating with a rotation period of about 27 days. And now this Coriolis force given by 2 omega cross V will be 0 in the polar regions where the convective blobs will have move up and down parallel to the rotation axis. But at lower latitude, certainly this Coriolis force will be non-zero and would deflect the convective blobs. So making convection somewhat less efficient at lower latitude. So if convection is more efficient at near polar latitudes, so certainly we expect that the poles may be slightly hotter, and with higher temperature there may be higher pressure, and that may try to drive flow like this, giving rise to a meridional circulation like this. So this is one simple way of producing meridional circulation. But wait a minute, don't we have meridional circulation in the sun in the opposite direction? I should say that this kind of a flow is called thermal wind, driven by this temperature gradient with latitude. So but this seems to give a circulation in the direction opposite to what is observed. So that means that we need to have another different mechanism for producing meridional circulation, which has to overcome this thermal wind and drive the meridional circulation in the opposite direction. So what can be this different, the other mechanism? To explain that, first I have to say a few words about the differential rotation, because this other driving force arises out of the differential rotation. So it was known for a long time that the sun's equatorial region, that the sun does not rotate like a solid body, but sun's equatorial region rotates faster than the polar region. So it was actually discovered by Richard Carrington in the 19th century. So one major recent development in astrophysics is that helioseismology has been able to produce a remarkable map of the distribution of angular velocity underneath the sun's surface. So here I show this map, and this blue color corresponds to higher angular velocity near the equatorial region, and this blue color corresponds to lower angular velocity. So how can this kind of differential rotation be produced? One obvious idea is that maybe these hot blobs of plasma rising or cold blobs of plasma sinking, they conserve angular momentum when they are moving. If that is the case, then angular momentum will get well mixed in the convection zone, resulting in a sort of a constant angular momentum per mass throughout the convection zone. So if that is the case, then we would expect omega to go as 1 over rho r square, where r is the distance from the rotation axis. But if that is the case, then we would expect the equatorial region of the sun, which is further away, to have a lower angular velocity. But observationally, we see the opposite of that. So certainly this is also not the correct explanation. So we need some kind of a mechanism to create a flux of angular momentum outward. So if we can put some angular momentum in this dump it in this equatorial region, then only the equatorial region will start rotating faster. So how can we produce this kind of flux of angular momentum? So the crucial paper on this subject was written by Lebedinsky in 1941. So the circumstances under which this work was done, those were really dramatic. So Lebedinsky was a young graduate student working in St. Petersburg, which used to be called Leningrad at that time. And 1941, that was the time of the Second World War, and Hitler's army was besieging this Leningrad. And some of you may know that eventually the Russian Red Army repulsed this attack, and that was a turning point in the history of Second World War. Anyway, at the time when Lebedinsky was doing this work, this city was under siege, and there was a scarcity of food and other items, and the future of the city was completely uncertain. Even in that sort of a difficult situation, working without any guidance, Lebedinsky developed this idea how turbulent stresses in the convection zone may transport angular momentum. And in honor of his, this effect was later named lambda effect by Rudiger. So lambda is a Greek letter corresponding to L, this first letter of Lebedinsky's name. So let me explain a little bit about this basic idea of Lebedinsky. So certainly angular momentum involves this component v phi of the velocity. And if we want to find out the radial flux of angular momentum, that would involve rho vr v phi. And now within the convection zone, we can have up and down motions, radial motions, or also it's possible to have this kind of horizontal motions. And suppose we are looking at the sun from the polar region, looking down the rotation axis. So the sun is rotating in this fashion. So you can easily convince yourself that if a hot fluid blob is rising, then the Coriolis force would make it get deflected in this way. And if a cold blob is sinking, that will be deflected in that way. And you can easily see that for these kinds of motions, rho vr v phi is negative. And if that is the case, then you have a negative flux of angular velocity, angular momentum, which means that angular momentum goes downward, making the equatorial region rotate slower. On the other hand, if you have horizontal motions in the convection zone, then you can easily convince yourself that the Coriolis force would divert this horizontal blob of gas to move either this way or that way. And in this situation, you can easily see that rho vr v phi is going to be positive. And if it is positive, that will drive flux of angular momentum in the outward direction, so that the equatorial region will get speeded up and would rotate faster. So if we want equatorial region of a star to rotate faster, then we have to have this kind of a horizontal motion more dominant over this radial motion. But is that possible? We may naively expect that those convective motions would be up and down, and that is the case when a star is slowly rotating. But if the star is rotating faster, then things change. And then the convection cells become much more complicated. They have a cylindrical shape, and they're often called banana cells or things like that. And they are in conformity with something called Taylor-Proudman theorem in fluid mechanics, that in the presence of strong rotation, fluid phenomena tend to be aligned parallel to the rotation axis. And if convection takes place in this manner in a rapidly rotating star, then you will see that there will be quite a lot of component of horizontal motion. And in this situation, angular moment, there can be an angular momentum flux outward, making the equatorial region rotate faster. So we expect that in the slowly rotating stars, the up and down motions will be dominant, and then there would be less angular velocity near the equator. But in the case of rapidly rotating stars with this type of convection, there would be angular momentum flux outward, and there will be more angular velocity near the equator, which is the case for the sun. And I can mention some of the historical landmarks in this field after this Lebedinsky's famous work. So Kippenhahn solved the Navier-Stokes equation for a rotating star using an anisotropic viscosity tensor. And as you all know, that the effect of convection can sometimes be captured by introducing a turbulent viscosity. And for the case in which the radial part of viscosity is more larger than the horizontal part, which will be the case if the up and down motions are more prominent. Then Kippenhahn found that there would be slower rotation at the equator, and on the other hand, if this VR, if this radial part is less dominant than the radial viscosity is less dominant than the horizontal viscosity, which will happen for horizontal fluid motions, then you get faster rotation at the equator. And then Kichatinov and Rudiger developed an elaborate mean field theory of these large-scale flows of by averaging over convection. So this theory they applied both to differential rotation and meridional circulation. And in the last few years, quite a lot of impressive simulations have been carried on. So one important simulation was done by my former student Vidya Karak when he was Nordita postdoctoral fellow. So he confirmed these things that if a rotating star is rotating slowly, then you have an antisolar angular velocity profile with the equator rotating slower. But if the rotation is increased, then it changes to solar profile with higher angular velocity near the polar regions. And I may mention that all these theoretical models of differential rotation, it also produced meridional circulation as a byproduct. So before coming to this crucial question, why differential rotation gives rise to meridional circulation, let me show you some results of differential rotation. So several years ago, some of us, Karak, Kichatinov and Choudhuri, we were trying to develop models of stellar dynamos. So when you develop a model of the solar dynamo, you can use the differential rotation, which is measured by helioseismology. But for stars, we do not have this kinds of measurement. So we first have to calculate this differential rotation of a star if we want to build a model of the stellar dynamo. For that, we have to use this mean field model of Kichatinov and Rudiger, where I have shown the equations, which are rather complicated, but I shall not discuss them. So by solving this equation, we got this kind of differential rotation for stars rotating with different rotation periods. So the rotation periods are indicated at this corner. So if you have a slowly rotating star with a rotation period of about 30 days, then we found that this angular velocity would be constant over, roughly constant over cones, as we see in the case of the sun. But if the star is made to rotate faster with a rotation period of 1 day, then we find that the angular velocity is constant over cylinders rather than over cones. So that is a sort of a general result, which is also confirmed by simulation. So now I come to the crucial question, why the differential rotation would give rise to the meridional circulation. So from the basic equations of fluid mechanics, if you derive this equation of phi component of vorticity, then the equation looks like this. So you see that there will be two source terms. One source term is like this, which is the thermal wind term, which I already discussed, that if the polar region is hotter, that will drive meridional circulation. That is the thermal wind. And this other term involves omega square. And you all know that the expression of centrifugal force involves omega square. So the appearance of omega square in this term is a telltale sign that that this term may have something to do with centrifugal force, and that turns out to be the case. So this term is called a centrifugal term. So let me try to give a physical explanation how this centrifugal term arises. For that purpose, you consider a straight line within the convection zone of the sun parallel to the rotation axis. Now, with the kind of differential rotation which is measured by helioseismology, you would find that the angular velocity here in this region is much stronger than the angular velocity in this region. And if that is the case, then a centrifugal force would be larger here compared to centrifugal force here. And now if you subtract the average centrifugal force along this line, then this remainder centrifugal force after subtracting the average, that will be outward in this region and that will be inward in this region. And that would clearly drive a meridional circulation in this sense, which is the direction in which we see meridional circulation in the sun. So basically, we can come to the conclusion that this meridional circulation has two driving forces. One is the centrifugal turn, which gives the meridional circulation in the direction in which it's observed, and another is a thermal wind turn, which would give opposite kind of meridional circulation. So we expect that the centrifugal turn may be the dominant turn, which is driving the kind of meridional circulation which we observe. But one may raise the question: is it possible that the thermal wind term is altogether zero, which will be the case if there is no temperature variation with latitude? So in that case, there would be centrifugal turn alone, and that would give rise to the meridional circulation in the correct direction. But this problem is that from this differential rotation measured by helioseismology, you can estimate the centrifugal turn, and from a back of the envelope calculation, you can show that if the centrifugal turn alone was present, then the meridional circulation would have been several orders of magnitude stronger. So why is the meridional circulation so weak? That problem is often called the small Taylor number problem. So the usual resolution of this problem offered by theorists is that this thermal wind term and centrifugal term, they are almost equal in strength. The centrifugal term being only slightly stronger than the thermal wind term, and that's why the centrifugal term drives a sort of a weak meridional circulation. And if you want to make the thermal wind turn comparable to the centrifugal turn, then you have to make the pole a little bit hotter. So Kichatinov and Rudiger estimated that the pole will be about 5 degrees hotter. So a little later I shall make a comment on that. So basically, within the convection zone, if these two large terms are very nearly equal to each other, then we get what is called the thermal wind balance equation, which says that the centrifugal turn should be equal to the thermal wind turn. And now we can, so you can see that there is this intimate connection between differential rotation and meridional circulation. That is, differential rotation gives this centrifugal turn which drives the meridional circulation. And now this intimate connection is I shall illustrate this intimate connection between these two large-scale flows more by considering what is called the near surface shear layer. So if you look at the map of angular velocity produced by helioseismology very carefully, then you will see that there is a region just below the surface around here within which the angular velocity falls radially by something like 5% over a small depth. And the question is, what produces this near surface shear layer? So this shear layer superficially resembles a viscous boundary layer with which most of us are familiar in our everyday surroundings. So I wonder whether you ever bothered about the question is why dust particles collect on the fans of on the blades of a ceiling fan. So you know that the ceiling fan is revolving and it drives the wind, and so you expect that this wind would blow the dust particles. So why do they collect on a ceiling fan? The reason is that this experimental fact that next to a solid surface, a fluid has to be always to be at rest with respect to it. So if you try to start a fluid flow next to a solid surface, then you will find that a little bit away from the surface there can be a strong flow, but exactly at the surface the velocity has to go to zero. So you have to have a layer in which the velocity changes from zero to a large value. This is called a boundary layer. A study of such layers is very important in fluid mechanics. And you know that fluid flow is governed by this Navier-Stokes equation. And if the viscosity is small, then you can usually neglect this term within the body of the fluid flow region. But even when viscosity is small, within the boundary layer, this term del squared V can become very large. So this term can be appreciable. So one believes that is the physics of the viscous boundary layer, that outside the viscous boundary layer you have this term is zero. So if this term is zero, then we call this part of the equation as the Euler equation. So outside the boundary layer we have this Euler equation, and inside the boundary layer this Euler equation breaks down because of the importance of the viscosity. So for many years, many solar physicists thought that this near surface shear layer is also something like that, that within the convection zone we have this thermal wind balance equation holding, and maybe at the top layer this viscous term becomes important, and the thermal wind balance equation breaks down, and that gives rise to the near surface shear layer. And though this idea was mainly hand waving, nobody was able to do any rigorous calculation based on this. And certainly we cannot think of any obvious reason why this boundary layer will be created. So there is certainly no solid surface at the solar surface. So some of us felt that this could not be a correct explanation, and we need to look for an alternative explanation. And here I show a photo of the solar surface, and you see this granular pattern. So these granules are essentially convection cells of the solar surface, which have typical sizes of about 1,000 kilometers and lifetime 10 minutes, which is much shorter than the rotation period of the sun, 27 days. So if the convective turnover time is so small, then we don't expect that this convection cells to be affected by solar rotation at all. But we believe that if we go deeper down below the surface layer, where the scale heights, various scale heights are much larger, then convection cells there would be of much larger size, because they are expected to be of the size of various these scale lengths. And if this much larger convection cells should be affected by solar rotation, the Coriolis force. So we can conclude that this Coriolis force has large effect on convection cells deeper down, but it would not have much effect on convection cells in a thin layer near the surface. And we believe that some of us now believe that this is a effect is crucial for producing the near surface shear layer. So if there is at a particular radius, or if there is a variation of temperature with latitude, then we can write this temperature at latitude theta in the form of temperature of at theta 0, which is the polar axis, and plus departure from that value of temperature delta T. Now this TR0 is the temperature distribution along the polar axis, where we pointed out that the Coriolis force would be 0. And now we have what are called standard models of the solar structure, from which we can calculate the temperature distribution when in the absence of Coriolis force. And so TR0, we expect that will be the temperature distribution given by the standard solar model, and delta T is the value of the temperature at a point by how much it would differ from the standard solar model. And we are making the simplifying assumption that in a top layer above some radius RC, there is no effect of rotation on convection. So if that is the case, then in this top layer, radial gradient of temperature will be independent of latitude. So we should have this kind of a relation. And if this expression of T, if you put in this relation, then you can come to the conclusion that in this top layer, this temperature, this temperature perturbation delta T will not change with R. So we can write this delta T in this layer in this fashion. So since it is not changing with R, so at some arbitrary value of R, it should be equal to what was the value of a delta T at RC at the bottom of this thin layer. And now we are ready to explain, give an explanation of this near surface shear layer. So the thermal wind balance equation we can write in an appropriate form like this. So on this side you have this centrifugal term, and on this side the thermal wind balance term. And if, as I pointed out, that in this top layer, we expect that delta T would be independent of R, so it will not change with R. And so that means that within this top layer, R larger than RC, this quantity del theta of delta T does not change with R, but in that layer, the temperature falls sharply, because the temperature at the solar surface is lower than what the temperature is in the interior. So in this top layer, this quantity does not change with radius, but the temperature appearing in the denominator here drops sharply. And that will make this right hand side of this equation very large near the solar surface. And if this right hand side becomes very large, then the left hand side also has to become large. And how can it become large? It can become large if there is a large variation of omega in this layer. And I suggested that this is how the near surface shear layer is produced. So I gave the basic idea in this paper and did some order of magnitude estimates and to show that this idea works. So at that time, I did not have any student working with me, so I was not planning to do any detailed calculations using this equation. But I was pleasantly surprised when Vibhuti Jha, who was a student of Dipankar Banerjee, contacted me after seeing this paper. So in this paper, I suggested this possibility of this detailed calculation. So he told me that he would be willing to do this detailed calculation if I was ready to supervise him. And of course, we needed the permission of his supervisor, Dipankar. So Dipankar not only readily gave the permission, but he also actively took part in our initial discussions. But after the work was done, when we were writing the paper, he graciously told us that we should not include him as a co-author because he could not take part in the actual calculation. So in this Jha and Choudhuri paper, we presented the structure of near surface shear layer calculated by Vibhuti. So he would basically we would assume that that omega inside the convection zone is given by helioseismology, and then in the top layer we would calculate the distribution of omega by using this thermal wind balance equation. And for that, we have to assume some value of RC above which we are assuming that convection is not affected by rotation. So here are the results for different assumed values of RC. And you can see this RC is indicated by this sort of a dashed circle, and the solid lines. So these are the various plots for different values of RC, and the solid lines give the contours of constant angular velocity we got from our calculation, and the red dashed line gives the results of helioseismology. So you can see that the fits are quite good, and in fact for a value of RC 0.96 solar radius, you find that our theoretical plots or curves almost fall completely on these observational curves of helioseismology. And here I have shown this percentile error in this top layer for this value of RC 0.96 solar radius. So percentile error is the discrepancy between theory and observational value. So you can see that apart from the very top within this layer, I think percentile error is typically, I think, less than something like 2%, which is an amazing result that gives us confidence that our theoretical idea is correct and we are on the right track. So apart from providing the first detailed quantitative model of the near surface shear layer, our model could make two clear predictions that the solar rotation should not affect convection above this something like 0.96 solar radius, and maybe within the next few years, either for helioseismology or more numerical simulations, we shall get some support for that. And another conclusion is that this pole of the sun should be about 3 degrees hotter. And the question is, can this be measured observationally? And it turns out that it is a much more difficult measurement than you may expect at first, because the temperature on the solar surface is not very uniform. We have these convective granules, and temperature at the centers of the granules that is much higher than the temperature at the intergranular length. So this variation of temperature is much larger than 3 degrees Kelvin. So at a particular latitude, you have to figure out what is the average temperature, and then you have to see whether this average temperature is changing with latitude. And these measurements become particularly difficult for the polar regions, because that is due to line of sight effect that appears at the solar edge. So the measurements are more difficult, but still there are some groups who try to, in the past, tried to do measurements whether there is a pole equator temperature variation on the sun, and some of these measurements suggested that there are maybe slightly hotter poles. You can see that this paper was written in 2008. So I am not aware of any further such study during the last 14 years or so. So most probably using the present day technology, it should be possible to do more careful measurements, and I hope that some group will undertake this type of measurement in the near future. So I now come to the last topic of my talk about this periodic variation of meridional circulation with this 11-year cycle. So I mentioned that this meridional circulation plays a very important role in the dynamo process, though I did not get into the details of that. But we also expect that the dynamo generated magnetic field will also react back on the meridional circulation. And Chow and Doi were the first authors who reported a variation of meridional circulation in the solar cycle. And here I show a figure from a paper by Hathaway and Reitmeier. So at the bottom of this figure, you see how the sunspot number has varied with time, and at the top you see this variation of amplitude of meridional circulation at the surface. So you can see that the meridional circulation became weakest at the time of the maximum of the sunspot cycle. So how does that happen? So at the time of the maximum of the sunspot cycle, we expect that there will be a strong belt of magnetic field like this at the bottom of the convection zone. And you all know that the magnetic field has tension associated with it. So a belt of magnetic field like this would try to shrink due to this magnetic tension, like a stretched rubber band. And this belt of magnetic field can shrink only by moving in the polar direction. So there will be a force in this polar direction arising from the Lorentz force of this magnetic field belt. And remember that the meridional circulation at the bottom of the convection zone is in the equatorial direction. So this Lorentz force will oppose this meridional circulation and try to weaken it. So this mathematical theory of this was what like Gopal Hajra and me. So we basically split the velocity field into two parts: the unperturbed part, which does not change with time, and a perturbation term, which perturbation part which changes with time due to this Lorentz force. And then the vorticity also can be broken up into the perturbed and unperturbed and perturbed part. And then we can, from our theory, we can derive equations for the unperturbed part, omega 0, and perturbed part, this omega 1. And in the unperturbed part, you find that this term, the centrifugal term, and this thermal wind term. And this thermal wind term makes the problem particularly difficult because you need thermodynamics to evaluate this term, and that is something extremely complicated. But the nice thing is that in the equation for the perturbed part, this complicated thermodynamic considerations go away. So we just have this equation where Fl is the Lorentz force and F nu is the force arising out of viscosity. So since this is our central equation, I have written this equation here again. So this is the equation we have to solve with this Lorentz force, expression of Lorentz force given by this, and this viscous force given by that. So you see that the Lorentz force, expression of the Lorentz force involves a magnetic field. And to get this magnetic field, we have to solve the dynamo equation, which I have not discussed in this talk. So, but basically we have to solve this equation of perturbed vorticity along with the dynamo equations. Then from the dynamo equations, we can get the magnetic field and calculate this Lorentz force term at every time step, and then we can solve this vorticity perturbation equation. And here I show the final results which we got. So this may appear like a busy slide, but it is actually not too complicated. So on this left side, we have plotted the unperturbed vorticity. So if the meridional circulation is poleward at the surface and equatorward at the bottom, then you can convince yourself easily that this unperturbed vorticity will be negative in the northern hemisphere and positive in the southern hemisphere. And here we have plotted the plots of various quantities as they are changing with time. So in the top row, we show this magnetic field B, the toroidal magnetic field at the bottom of the convection zone, how it evolves with time. So here I think this second one is the plot for the epoch of when sunspot maximum. So at that time you can see that this B is the strongest, and then this is the minimum when this B becomes weaker. And this is the plot of the Lorentz force, which appears in our perturbation equation. But finally, we get this perturbed vorticity. It's how it varies with time in this fashion. And if you look at this perturbed vorticity at the time of the sunspot maximum, then you see that it has a sign opposite to the sign of unperturbed vorticity. That means that at the time of solar maximum, the perturbed vorticity opposes the unperturbed vorticity and makes it a little bit weaker. And at the time of sunspot minimum, it tries to reinforce it. So as a result of that, we get this kind of a plot, and when at the bottom you have the theoretical sunspot number from our dynamo equations, and then the vorticity equation gives you that the meridional circulation at the surface will vary in this fashion. And this plot has to be compared with this observational plot, and you can see that we are able to explain the basic features. but not everything completely. So in this observational plot, it seems that meridional circulation becomes weakest at the time of sunspot maximum, whereas we find a little bit of a phase difference of something like 1 or 2 years. So presumably, though we are in the right direction, but presumably we have not got the complete theory. And another worry is that in our following this perturbation approach, we found that the velocity at the bottom of the convection zone perturbed velocity turns out to be about 50% of the unperturbed value. So that raises the question whether one has to go beyond the perturbation approach. But even this perturbation calculation was quite complicated, so we are happy that we did the first this calculation of this kind, and now we other people should do the more complicated, more complete calculation. So I may mention that this work was the main part of Gopal Hajra's PhD thesis, which was selected for PhD at Large Award by the International Astronomical Union. So Gopal was the first Indian to receive this very prestigious international award. Okay, so with this, I have come to the end of my presentation. So now I put the conclusions before you. The sun has a meridional circulation, which is from equator to the pole at the surface and from pole to the equator at the bottom of the convection zone, which is now measured by helioseismology. And it seems that this meridional circulation is driven by the centrifugal term due to sun's differential rotation, which is nearly balanced by this thermal wind term. And this theory of differential rotation is intimately connected with the theory of meridional circulation, which was beautifully illustrated when we discussed how we develop a theory of near surface shear layer by solving the thermal wind balance equation. And then finally, I discussed the periodic variation of the meridional circulation with the 11-year sunspot cycle and how it can be modeled as arising from the Lorentz force of the dynamo-generated magnetic field. So, thank you.
Thank you, Professor Choudhuri, for this kind of amazing journey that you took us through, right from defining what is meridional circulation to what causes circulation and what are the competing forces in terms of centrifugal term and thermal wind balance term, and how the helioseismology addresses this, answers or gives some kind of guidance to the theories to come up, and finally the perturbation approach that you have applied to address these issues. And last but not the least, congratulations to you and your student, Gopal Hajra, for this wonderful work. And it's been really whatever you presented in this hour or so is a great treatise for people or solar physicists who are looking at the basic dynamics of the sun. And so it's really a pleasure that you have. It's very educative that you have given us this very nice lecture, and definitely this really commemorates Dr. Arvind Bhatnagar's contributions in terms of initiating the helioseismology work at Udaipur, being a part of the whole gong chain. So it's really befitting, and the nice gesture and the nice results that have come out of it. Thank you very much for this wonderful lecture.
Yeah, thank you.
And I will now request my colleague, Dr. Avik Sarkar, to please carry out the question answer session. Avik, please.
Yeah, thank you. So thanks, Professor Rai Choudhuri, for your wonderful talk. I'll take now questions from the WebEx platform first, and then I'll take questions from the YouTube. So if you have any questions, can you please raise your hand by clicking raise hand at the bottom of the WebEx. Meanwhile, I may ask you a question. I have plenty of questions basically. So, if I ask you, if I can ask you that, you have shown that turbulent stress can take the angular momentum away.
Yes.
And likewise, when you start introducing magnetohydrodynamics or magnetic field in your calculation, Maxwell stress also can take some amount of
Yes.
angular momentum away. So how is above the 11-year cycle, you may have some other effect onto it.
Yeah, that's an interesting question. For example, you know that this magnetic stresses taking out angular momentum. That's a very important effect in the solar wind. So we believe that the early sun in the earlier times was rotating faster. So this question is whether this effect is important within the convection zone or not. So in the last few years, as I pointed out, the several numerical simulations have been carried out to study this angular momentum transport within the convection zone. And some of these simulations are purely hydrodynamic simulation, whereas some other simulations are MHD simulations, including the magnetic field. So whether it's a purely hydro simulations or a simulation with a magnetic field, you get somewhat sometimes you get somewhat different results, but they are, as far as I know, they are qualitatively similar. But that's my understanding, that the results do not change very drastically. But it's a subject which is in which I think somebody like Vidya Karok has worked. So maybe you should he would be more qualified than me to answer this question.
Okay. Okay, I'll take some of the questions which are posted here already on the WebEx platform. So, why more sunspot activity occur in the solar surface through meridional circulation?
Okay, so do I understand the question is why there are usually more sunspots at the middle latitudes rather than we don't see sunspots at the very high latitude? So that is a question which is connected with the dynamo theory, this dynamo process, how magnetic field of the sun and sunspot cycle is produced. As I said, that is a very I think subject which is very, I think, close to my heart, and I have on many occasions I have given talks on the solar dynamo, but today I decided that I shall give a talk on a different subject. So to address that question, it will take me too far from what I have discussed in today's talk, but maybe at the end of this other questions are over, maybe the person who asked this question, if he wants to stay back, then I can have a more discussion about that at the end.
This is again the same question, Dr. Rakesh Kumar Mishra. So he's again asking, what are the important predictions through dynamo model?
Okay, again, that is talks something outside the scope of this colloquium. So I have been involved in this prediction of sunspot cycle with the dynamo models quite a bit, and my citation for Chandrasekhar Prize also mentioned that. So I would be happy to discuss that, but that is a topic which is rather far away from what I have been discussing today. So again, if there are other questions, I shall take them up, and maybe I can have a private discussion with Rakesh afterwards if he is interested.
He has plenty of questions here. So Professor Hariam Vats, he's asking, does the meridional, very nice talk, first of all, does the model explain north-south asymmetry of differential rotation? And two, temporal variability of north-south asymmetry?
Okay, so the north-south asymmetry is for the differential rotation. To the best of my knowledge, there is a north-south asymmetry is very small. but in the meridional circulation, it's believed that there is a more prominent north-south asymmetry. And because this meridional circulation comes from a small imbalance between two large terms. So if it comes from imbalance between two large terms, and because of the convection and turbulence in the convection zone, these terms are expected to have fluctuation. So if these two large terms, if they have a fluctuation, then we would naively would have expected more fluctuations and variations in the meridional circulation. So it's actually a puzzle rather than explaining how this there may be asymmetries and fluctuations in the meridional circulation. So it's a more challenging question is to explain why this meridional circulation has so little fluctuation. We may naively expect that if it comes from the small imbalance between two large terms, then there will be much larger fluctuations. So we still do not have a very good understanding why these fluctuations in meridional circulation are not even larger than what we see.
Okay, thank you. May I ask Ananya to ask question?
Hello?
Yes.
Am I audible?
Yeah.
Yes.
Good afternoon, sir. Thank you for such a nice talk. Sir, I would like to question that since the sunspot are considered as perturbations, so if the number of sunspot increases, so in certain cycles the number of sunspots are more, and in some cycles the sunspot number are less. So does the number of sunspots would affect the that 11-year cycle? So if the number of sunspot are more, then the cycle would be around 10 years, and if the sunspot number is less, then the perturbation would be less. So would that affect the years of that sunspot cycle?
No,
Yes,
actually, it's
if I can.
interesting that the effect is opposite. Again, it is outside this scope of today's lecture. But since you raised this question, so actually it's opposite. It turns out that the stronger cycles have a shorter duration and weaker cycles have longer duration. So it is there is something called Waldmeier effect, which is known for nearly a century. So anyway, again, that is somewhat outside today's lecture, but we in our group we have worked on Waldmeier effect and how to explain that. So with the Karok we did some work on this about 10 or 11 years ago.
Okay, so but the convection is not affected by these flows, but when it comes to magnetoconvection, so how does these meridional flows affect the magnetoconvection happening?
Well, meridional circulation, that is, I think, intimately connected with convection. So as I pointed out, that it's turbulent stresses in the convection zone which drives the meridional circulation. So they are intimately connected.
Okay, thank you.
So there was a question, which type of instrument used to predict solar dynamo? Is it through computer simulation or sunspot or solar spectrum, which are good to predict solar activity within the sun?
Well, I think we should have this both complementary approach. We would have both, I think, observations and theory. So observations with surface observations and helioseismology results from interior of the cycle, and also in theory, both I think the kind of mean field models which I have worked on, and some of this numerical simulation. So since it's a complicated system, we need a combination of different approaches.
I don't see any question. I have again another question. In atmospheric science, you see Hadley cells.
Yes.
So because of this differential heat flux. So how can you, I mean, how much do you expect some sort of physics from this common physics in both of them?
Okay, so I suppose that there is a, for example, there's a thermal wind balance equation which we have used we have used in our calculation. So it is very little known within the astrophysics community, but I hear that this thermal wind balance it is known quite a bit in the atmospheric science community. So at the beginning, I introduced this meridional circulation by giving this example of atmospheric circulation. But there I make a sketch of a very simple sort of atmospheric circulation. As far as atmospheric circulation is more complicated, has more cells, and I do not know the details of it. So since PRL being a place which is strong in atmospheric science, so probably there are maybe persons who are more qualified than me to answer these questions. And it is a very interesting question to what extent there are physics of meridional circulation in the Earth's atmosphere and in the sun, how they are analogous. And somehow in the last few years, I did not have any opportunity of discussing with this with atmospheric scientists. So maybe we should, atmospheric scientists and solar theories, we should talk to each other.
Professor Pallam Raju has a question.
Yes. In fact, I'm not from the solar physics field, but I was curious to know when you ended the talk, with saying that, you have introduced the perturbation approach and it has come to some success, but there are many more things to be done. What are the things that probably, you can point on so that it may be useful for the younger scientists to take up?
Okay, with respect to this particular
Yeah.
problem?
Yes,
Okay.
yeah, this particular
Okay.
problem.
So it was since it is a somewhat of a complicated subject, we made some simplifying assumptions. So one simplifying assumption we made was that that there is some radius RC above which this convection is not affected by rotation, and below it this convection is affected by rotation. So this is certainly not a sharp transition. That is I think a more gradual transition. But we made this simplifying assumption to make the calculations manageable, and then so it's a difficult question how to go beyond this and make it more realistic. Maybe other people will have ideas which had not occurred to me, and I expect that maybe from helioseismology or other things there would be inputs. And also this instead of a perturbation approach, whether we can try to solve the full thing numerically. And my skills for numerical calculations are more limited, but maybe some other people who are better than us in numerical calculations may try to do the whole problem through numerically without following this perturbation approach. But this main beauty of this perturbation approach is that that is a thermodynamic term, the thermal wind term, which makes the problem very complicated. In the perturbation approach, for the equation of the perturbed quantities, we could get rid of this thermal wind term, which made the calculation simpler. But if you don't follow this perturbation approach, then you have to handle the thermodynamics also appropriately, and that makes the problem complicated. So as I said, that we since we are among the first people to study this problem, we could do the first steps, which are still complicated enough, but maybe others will be able to figure out, have ideas which had not occurred to us, how to make these models more realistic.
Okay, thank you. Thanks for your thoughts. I just wanted to, because you brought out nicely about the perturbation approach, and you rightly said as much as possible that was done. But then when you ended that, that there are more, younger people can take out. So take further. So I was just curious. That's it. Thank you very much. Thank you again. No, it's been very fascinating listening to you again, as usual. Thank you.
Thank you very much. We are already close to 5:30, so I would ask Rajesh to close the session.
Thanks, Avik.
Girjesh, just a second. I noticed that Dr. Bhatnagar's daughters are here. I would like to welcome them, although it's a little late. So Dr. Tripti Bhatnagar and Malvika Bhatnagar, thank you for joining us for this lecture. If you can listen and if you have anything to say, you can. If you have to ask a question, you can.
Yeah. Hello.
Yes.
Yeah. A very good evening to everyone from PRL and USO. And it has been a very nice lecture. I'm a biological scientist, so maybe I did not understand a lot of things, but it was very beautifully conducted. And I think so, Dr. Choudhuri, what he told about my dad was, he was always very motivational. I think he having 3 daughters, and we have really been at his heart how he told us how to grow forward, how to go forward. For everything, he was always pushing us. So I think he had that inbuilt, a scientific caliber of motivating people and getting to do allowing them to do what they really wanted to do and grow in that field. So even though all my sisters, actually 3 of us are not into physics or astrophysics, but we are there with PRL and USO for any function or any celebration of this kind. So thank you. I would really like to thank you, PRL and USO, for conducting this special lecture. And thank you, Dr. Arnab Choudhuri. It was great to hear you. Thank you.
Thank you, Tripti. Thanks a lot.
Yeah.
Good evening to all of you. So that brings to the concluding session for today's second Dr. Arvind Bhatnagar Memorial Lecture and PRL's Amrut Vyakhyaan. On behalf of PRL and the Vyakhyaan Committee, I would like to thank Professor Rai Choudhuri for accepting our invitation and delivering this wonderful presentation on fluid flows inside the sun. And also, I would like to thank Professor Rai Choudhuri for taking the questions from our audience and answering them enthusiastically. I would also like to thank our audience for joining us on the WebEx and also on the YouTube platform and attending this presentation. I sincerely thanks our director, Professor Anil Bhardwaj, Professor Pallam Raju, the Dean PRL, Professor Anita Srivastav, Chairperson Vyakhyaan Committee, for their continuous support in organizing these Vyakhyans periodically. Also, I would like to thank all our members of Vyakhyaan Committee for their continuous effort for conducting this Vyakhyaan every week. Thank you so much. And at the end, I thank everyone for being with us on this our celebration of this Azadi Ka Amrit Mahotsav and 75 years of PRL's birthday. So thank you so much for joining with us. Thank you all.
Okay, as I said that if Dr. Rakesh or somebody else wants to discuss with me, then after others log out, I can have a.
He's not available online. What I can see is that he's available on YouTube.
Okay. Yeah, then maybe on some other occasion.
Yeah, Dr. Rakesh, if you can listen to us, you can drop him an email. Then he can probably reply to your other questions and you can have more fruitful discussions. Thank you very much.
Okay.